Basics of Network Analysis. Inductors.
Hello all, welcome to my YouTube channel. Today we'll be continuing the discussion on network analysis and today's topic is inductor. Inductor is a very important passive electrical appliance which will be used in most of the devices and applications in electrical domain. Let us first understand its major applications. Most of us have fluorescent lamps in house. There will be always a big metallic device which will be there and will never understand what is that application. That is called a choke in electrical word. It is an inductor, so it's used in fluorescent lamp, and there is a major application of this inductor in turning on this fluorescent lamps. And second, inductors are used in many motors, and principle of inductors are used in transformers, and inductors are used in many power electronic applications like DC-DC converters, inverters, and many more. So, what are the major properties of these inductors, and why these properties makes them to use in this kind of applications? We'll understand one by one. Before that, what is an inductor? Inductor is a simple electrical coil, means a conductor which is turned into a coil is called an inductor. This is an inductor. So current carrying conductor, if is turned into a number of turns, then it will become an inductor. So let us understand the behavior of inductor. Before that, we'll first break down into few electromagnetic properties of inductor, some basic principles of Faraday's law. Any current carrying conductor will generate a magnetic field around it, and the direction and will be given by Faraday's right hand thumb rule. If you are holding a current carrying conductor in your right hand, then fingers represent the direction of current, direction of magnetic field, and thumb represent the direction of current. For this, if you are increasing the current of the current carrying conductor, your flux will increase. Means magnetic magnetic field will increase. If you are increasing the value of amperes, this flux will increase. If the same current carrying conductor is made into turns and placed similar way, then it will become an inductor. For this inductor, from the derivation of this single turn coil into various turns coil, the direction of the flux will be direction in the longitudinal direction of the coil. Means if this is the longitudinal direction of the coil, flux direction will be also same. So here also, if current increases in the coil, flux increases again with the same property of previous thing. But here there is one more trick. This inductor will behave differently for different sources, that we'll understand one by one. But majorly, if current increases in that coil, flux will increase. That is one thing. There is a, from the Faraday's law, there is a from the definition itself, we will understand one thing. If any current carrying conductor produces a magnetic field, and that magnetic field will will be in a such a direction that it will try to oppose the direction of the cause. Means, for example, if this is the inductor and you are producing a current because of some voltage source, current direction will be in this, and the induced EMF or the induced flux direction will be in such a way that it will try to oppose the direction of the cause. This is the cause of the flux direction. For example, this current is creating a flux direction in this way. This is the flux direction. Then the direction of the induced EMF will be in such a way that it will try to opposite the cause. The cause is this current. So direction of the induced voltage will try to produce a induced current, and that will produce an induced flux that will try to opposite this caused flux. So because of this reason, the flux should be always produce an induced EMF in this direction. This is the important property of Faraday's law, which is telling about the inductor. Any inductor means it will try to oppose the cause. So what is the cause? The current carrying the current which is flowing in the inductor is the cause, and that current direction will be opposed by an induced EMF. So that is the important property of the inductor. So this will describe one more important property, that if an inductor is connected to a voltage supply, so that voltage supply will draw a current high, and this current is opposed, always opposed by an induced EMF E, plus and minus. Current across the inductor will not change immediately. Means if you are applying any voltage or any kind of voltage to an inductor, its current cannot increase immediately. It will take time to increase. If this is voltage and this is current, current will always take time to build up. That is the property of inductor. That means rate of change of current di by dt is by inductor. So this is very important application. Current in inductor cannot increase rapidly. If you want to protect any electrical circuit for a current, then the best application is inductor. If you want to smooth the current profile, for example, an electrical circuit is having this kind of spikes, current spikes, and if this is treated with an inductor with a very good amount of inductance, then the inductor will have the current profile like this. Rate of change of current will be limited because of the inductor property. This is one of the biggest application of inductor. Now let us understand what will happen if inductor is connected to a different voltage sources. If inductor is connected to AC alternating voltage, what will happen? For example, the AC alternating voltage is V is equal to Vm sine omega t, and the inductor has inductance of L. So what will happen? It's a pure inductor. So if this kind of AC voltage is applied to inductor, inductor has a basic property that it will try to oppose the cause of induced EMF. So induced EMF, for example, if induced EMF is in this direction, and the cause will be the current, so it will try to oppose this cause. From Faraday's law, we know that induced EMF, this induced EMF E, is due to change in flux. So E is equal to d phi by dt, and flux is there is one more relation between flux and current, that will be total flux linkage is equal to inductance times current carried across the conductor. So flux is equal to L by N into I, and I is the current through the conductor. So substituting that, E is equal to L and N will be constant. So L by N into di by dt. So E is equal to L by N. This is V is equal to Vm sin omega t. Always induced EM will also will have similar waveform, that will be Vm sin omega t itself, to oppose from the Faraday's law. Or we'll simplify this by taking I is equal to, we'll have the current I is equal to Im sin omega t is the current. Because of this, what will be the current direction? It will be there. I is equal to d of vi d by dt of Im, and L by N is a constant, and derivative of this is the again constant. Derivative of sin omega t is cos omega t Im. Emf is Im into L by N, sine a differentiation cos. And if you want to write it again in terms of sine, how you will write sine 90 minus omega t, write it in terms of sine. So current which you took, I is equal to Im sin omega t, and voltage you got across the inductor Em sin 90 minus omega t. That means what? Current is lagging by 90 degree. This is very important property of inductor again. Current lags voltage by 90 degree. In any electrical application where you want to lag the current, then it is simply for that electrical circuit, inductor will be connected so that you will have 90-degree phase compensation. Very good, important application. And next, with this, next one more property we can describe if the same inductor is connected to a DC voltage source. For a DC voltage, when an inductor is connected, there is from magnetic properties of the inductor, the important thing is from the Faraday's law, induced EMF will be there only if there is a change in current. If di by dt is there, then only induced EMF is there. E is equal to L into di by dt is the voltage across the inductor formula. And to have this induced EMF, you need change in current. For DC voltage source, this di by dt will be 0. So induced EMF will be 0 for DC voltages. That means there will be no opposition. So if you are connecting a DC voltage source to an inductor, always the opposition will be 0. And as you increase the frequency, okay, and we got the equation also here, there one more. As you increase the frequency omega, the opposition offered by the inductance will be more. Means for AC voltage, the opposition by the inductor will be more than the DC voltage. So this is one important property. Inductor will pass only lower frequency and it will bypass the higher frequency when connected in series, and it will be in other way if it is connected in parallel. This is very important application of inductor in filter circuits. So that is one more property we understood. So now let us go to the concept of inductors in series and parallel. If inductors are connected in series, the mutual inductance, or sorry, the self inductance of the overall system will increase. If this has self inductance L1 and another coil has a self inductance of L2, overall inductance will be L is equal to L1 plus L2. And if this is similar to your resistive combination, resistive equivalent circuits. If same inductors are connected in parallel, then inductors total equivalent inductance will be parallel combinations of resistor 1 by Lp is equal to 1 by L1 plus 1 by L2. So this is the important application of inductance when connected in parallel. Let us summarize what we studied in today's session. One is the application of inductance di by dt. Inductance opposes di by dt. Inductor produces 90-degree current lag. Inductors are used in filter circuits. Next, series and parallel combination inductors. That's about today's session. If you like the video, please subscribe and continue with the learning. Thanks for watching.